Okay, so hello everyone. Welcome to episode 72 of Warsaw Quantum Computing Group Meetups. My name is Pavel. I will be the moderator today, and yeah, we have pleasure to host our next great speaker, Konrad Łącki. And Konrad will give us an introduction to the FPGA-based QUBIT emulator for physical simulations of quantum states. So Konrad, thanks for accepting our invitation. Just a few announcements before we start. This meeting is recorded, so hopefully the video will be later available on our YouTube channel. And if you have any questions during the talk, please post your questions on the chat, and there will be a Q&A session at the end where we'll have the opportunity to ask questions to Konrad. Before we start, I would like to thank our strategic partners for supporting us, Sonover R&D, Cogit, Quantum.io, QLab, Onyx, and QUBIT. And we'll also thank our honorary partners for helping us in spreading the information about this meetup. All right, I will stop sharing my slides now. And Konrad, if you are ready, the Zoom is yours, and you can start sharing your screen again.
Okay, thank you. I'll get everything set.
Konrad, you're muted now, just in case. I'm not sure if you are saying something, but
Oh yeah, I was just setting this up, and
okay,
I
nice.
hope everything is visible now. Is it okay?
Yes, I can see it now.
Okay, great. So, hi, I'm Conrad. Welcome. Today, I'll be talking about the qubit emulator for physical systems or physical simulations of quantum states offered by AIQ Lab. And I'll start off by introducing AIQ Lab. So, AIQ Lab is an initiative aimed to advance quantum technologies and also to educate and train through quantum laboratories. And actually, we conduct workshops with hands-on experiments on our quantum devices. Actually, just now, I'll try to switch over to a second camera angle that shows off two of those devices that compose the quantum laboratory. Just one second. Hopefully it'll go smoothly. Okay. Uh, there should be a second angle now. And yeah, on the right here, we have the qubit. And on the left here, it's a little bit big. So I'll move the camera just slightly. But on the left, we have the qubit laser manipulation system, or QLMS for short. And these two devices can be integrated to run some quantum experiments. Today, I'll be focused on the qubit. So let me change the camera right now. Okay. So I wanted to start off with the basics of quantum computing, just to understand a little bit better what the qubit is made for, what it is supposed to do. Let's start off with the quantum bit, or qubit for short. Simply put, this is a two-level system, whereas a classical bit can have either 0 or 1 as a as its value. A quantum bit can be in a superposition of both of these basis states. And the way we signify a quantum state, we use the Dirac notation shown over here. We have ket of psi, and that equals to 0 times ket of, or alpha times ket of 0 plus beta times ket of 1. So here, alpha and beta are the probability amplitudes. And the interesting thing about them is that they're in general complex, and they're correlated with the probabilities of getting either state 0 or state 1 after a measurement. I'll go over that a little bit later, but another very important thing to note here is that the state of a quantum bit can be represented on a unit sphere called the Bloch sphere, as shown on the right. In this coordinate system, we can use a theta and, oh, 1 second. Okay, so as we see on the right, the state is described by two angles, theta and phi. And using this coordinate system, we can write out the probability amplitudes accordingly. And the state of the quantum bit is described by the state vector, which has one end uh, fixed at the origin of the Bloch sphere, and the other end is actually confined to the surface of the Bloch sphere. And depending on the position of this state vector, we can denote the state of the quantum bit or qubit. Okay, so we have our qubit. What can we do with it? How can we manipulate it? How can we do operations on the qubit? Well, here come quantum gates. Just like classical gates, we have the NOT gate, OR gate, and so on. Here, when it comes to one qubit gates, we have in the top row the Pauli X, Y, Z gates, as well as the Hadamard gate. And on the bottom, we have our X, our Y, our Z gates, which are rotations along their about their respective axes. When we have our quantum gates, how can we visualize that on a Bloch sphere? Actually, it's pretty convenient. Whenever we have, let's say, on the top, we have our X gate being applied to state psi 0 that is currently in state 1. Once we apply that gate with an angle of pi radians, we see that it rotates the state vector about the x-axis. And we see that with this angle, we get 0 as a result. And on the bottom, we don't have to stop with one quantum gate. We can do more in series. On the bottom, we have the Hadamard gate, which is a little bit more complicated. Here, it is a rotation about an axis on the XY plane, about exactly 45 degrees from the X and Y axis. And it's actually a very special gate. It's used extensively in quantum algorithms, also in quantum error correcting codes. And in this case, it actually sets a qubit that is in one of its basis states, either 0 or 1, into an equal superposition. And we see after applying the Hadamard gate, the state vector is pointing along the equator. And that means that it is in an equal superposition. Another thing to note is that this list of one qubit gates is not exhaustive. Of course, we also have the phase gate, the T gate, but something to note here is that all one qubit gates can actually be reconstructed through the gates on the bottom, Rx, Ry, and Rz. Just as an example, the rotation, the first rotation, Rx of pi, that's actually equal to the X gate. And the Hadamard gate is a little bit of a more tricky decomposition. But yes, essentially, we can also use these gates to recreate the Hadamard gate. Okay, so we have our quantum bit, we can do operations on it, but unfortunately, a quantum bit does not stay quantum forever. A qubit, if left by itself, will eventually lose its quantum state after some time. or decohere. And what happens here? So after that, the qubit collapses into either 0 or 1, the values that a classical bit can occupy. And this is called the wave function collapse, and it is actually irreversible and also purely probabilistic. So once a qubit decoheres, it has some quantum state before, we have psi, and after that, according to its probability amplitudes, the square moduli of the corresponding probability amplitudes, it can collapse into either the 0 or the 1 state. And actually, when we want to measure our qubit, we have to inherently collapse its wave function. So it's more of a purposeful decoherence, you could say. But yes, whenever we measure a qubit, we acquire only 0 or only 1. Okay, so now we have the basics out of the way. I'll go into the qubit emulator. So what is the qubit device? Well, it's an FPGA-based quantum bit model. It uses the block sphere to represent the quantum state on a VGA monitor, as shown over here in the camera. I hope it's visible. But the way to manipulate the qubit, we connect our PC through an Ethernet connection to the generator meter shown to the right, and we control the qubit using UDP commands. Afterwards, these commands are encoded in the generator meter into precisely timed electric pulses, which are then sent to the qubit. And then the qubit returns pulses that decode its current state. So you may be asking, what is so unique about this solution? What makes the qubit emulator stand apart from other solutions? Well, other quantum simulators, they are cloud-based and purely based on a mathematical formalism. And because of that, they essentially circumvent a lot of the physical problems that are experienced when working on or building real quantum computers. And just as an example, when we want to make measurements of these electrical pulses, I mean, they are, in fact, susceptible to unpredictable physical noises. And as an added fact, it is also possible to inject physical noise into the system or use some internal physical noise. But I'll get into that in the next slide when I'll talk about the features. But not only that, also timing here is a great concern. The pulses take time. Their effect is not immediate. Yes, very fast, albeit not instantaneous, just like on real hardware. And as far as we know, we are the only ones offering such a physical qubit emulator. And yeah, as I've shown before, it's a physical system that you can interact with and do your quantum experiments with. So when it comes to the features, on the very top, as shown on the camera view, we have the block sphere, and on the right we have theta and phi. Currently, the state is in 0, 0 in the 0 state, but the state vector is shown in red. If we go a little bit below the VGA monitor, displaying the screen, displaying the quantum state, we can get into the qubit decoherence feature. And here a user can actually set the decoherence time, after which the qubit will stop acting quantumly and will collapse into 0 or 1. After this collapse, you're also able to set the quantum state back to a quantum state. It'll act quantumly. And yeah, there's also another feature that it offers, the qubit noise feature. Here you can set an internal FPGA noise to act on the state vector Or if you want, you can inject some external noise, for example, from a function generator, with the help of some BNC cables, and consequently, you will see the state vector being affected by that noise. And a little bit down towards the right, this is where we connect our Ethernet cable so that we can manipulate the qubit, do some quantum experiments, and communicate with our PC. So there's actually a dedicated Python library where you can do your quantum experiments with the qubit. It essentially just adds a layer of abstraction over the UDP-based commands that control the qubit. So actually any programming language that supports the UDP protocol can be used. What the library offers, it offers functions for communicating with the device, preparing the states, doing some gate operations, reading states, measurement, and many more functions also. Of course, you can use your favorite Python environment, be it PyCharm, Jupyter Notebook, so you can work very comfortably and do your experiments. And another way to actually do your experiments is through the qubit application. Here it allows for controlling up to 2 qubits simultaneously. Oh, and I actually forgot to add, when it comes to the Python approach, I believe it is up to 8 qubits currently at the moment. But with application, we have two, and it is comprised of 5 separate modules. The first one is called control qubit, and here you're able to set the state of the single qubit. You can read the state, perform measurements, and also reset the quantum state. The next one is called code editor, and here you can write penny lane code so that you can control a single qubit interactively. The next one is called Hamiltonian and unitary evolution. Here, you're actually able to evolve the qubit according to a defined single qubit Hamiltonian that you prepare. The fourth one that's being offered right now is the reupload classifier. Here, you're actually able to draw either a 0 or 1. The image then gets reduced to a vector, after which the result actually gets encoded onto the qubit, which is really cool. And the last one is the mixed states. Here, you're able to encode a single qubit mixed state using pure states of 2 qubits and classical probabilities. Okay, so I'll go over a couple of examples of experiments that you can do. First, I'll go over 2 experiments through the application. After that, I'll go over 2 experiments in Python. So here we go. The first experiment is the qubit control through the application. Here, as I said before, we'll be able to set the state of a single qubit, read the qubit state, perform measurements, and reset the qubit state. So here I will change this 1 second. And now I hope the application is visible, qubit workstation. So the qubit that we have right here happens to be qubit 1. Right now it is set to the 0 state, as can be seen, but we can change the theta value, let's say somewhere about here. Maybe let's also change the phase. Let's wait 1 second. Okay, and now let's click Set State on qubit. And as we see, we actually do get the qubit to the right data values. Here we have it in radians, and the qubit is displayed in degrees. And here we get the quantum state written out for us, calculated for us. We can also read the state. Here we go. And after that, we're able to measure the state. So we're expecting to get either 0 or 1. Let's see. Okay, so this time we measured the 1 state. And maybe you have noticed that right above the theta and the phi angles, there was this little icon in red that showed psi. Now it is gone. That means that now the qubit is acting classically. We can't apply any gates to it. And to actually redo that, we can click Reset State, and that icon should pop up any second now. Yeah, there it is. So this is the first experiment. Let's see. Let's go into the second one. Okay, so the second one will be the data re-uploading classifier. Here we will be able to draw either 0 or 1, after which we'll have to downscale the image. A PSA vector will be calculated, and based on that PSA vector, the result will be mapped onto the block sphere. We'll see that in action in just 1 second. Let's go back to here. Okay, let's go to re-upload classifier. All right, so I'm gonna draw as an example, let's say 1. I'll start off with 1. I have a 1 right here. The next step is to downscale the image. After that, the vector is created, and we will see if the state vector will be closer to 1 or closer to 0, if it recognizes it being a 1 or a 0. Let's see. Okay, so as we can see now, the state is for theta 139, and for phi it is 8.2 degrees. And also the probabilities are calculated here. And evidently, I did draw a very nice 1 here, so we were expecting a 1 to come out. And we can also try drawing a 0. Just 1 second. I'll reset all of this. Okay. Now we're back to the 0, 0 state. And let's start to draw the 0. Now we downscale the image. We get a different vector this time. And let's see if it'll be a little bit closer to 0 or 1. Okay, this time it's not nearly as close to the correct solution as before. However, probabilistically, there is a higher probability near 0. And yes, that is actually the correct solution. So now I will go back to the presentation, and we will go into the next experiment. Okay, so the next experiment will actually be a very similar experiment to the first one we did on the application, but this time we'll be doing it through Python. I'll go line by line, explaining what each function does. So first, we're going to connect to the qubit. Then we're going to set the state. We will read the qubit state, perform some measurements, and after which we will reset the qubit state. Okay, let me go back here. Okay, all right. So I have my code in Jupyter, and let's see what's going on over here. So the very first line, we're just importing all the functions from the dedicated library. Let's run that. Next, we have to set the time between the commands. I'll just be setting 0.1 seconds, and the device that I'm using right now is GenMet1. So let's see that. Okay, so the way to set up the state is by using this function over here. I will set the initial theta to be 45 degrees and the initial phase to be also 45. Let's see if it'll set it up. Okay, there it is. So now we see the wave vector corresponding to the state that I set. We can read the state. Let's see what gets printed. Okay, so we got 45, 45, just as expected. And next, let's measure the qubit. Okay, this time we got a 0. And if we want to reset the state, just as before, we will see the icon popping up on the screen any second now. And there it is. Now that we have the qubit in a quantum state, why not just apply some gates to it, just to show how the workflow goes. So here I have the Hadamard gate, and to the 0 state, let's see what happens. And yes, now it's at 90, 0, just as shown before. And let's rotate it along the z-axis, about the z-axis by 45 degrees. Okay, there it goes. And even though the phase is non-zero, we are still in an equal superposition. So now we can actually measure again, and we have half probability of getting 0 and half of acquiring 1. Let's see what we get. Okay, so we got 0 once again. If we want to apply any more gates, we will set up the 0 state. If we also want, we have another function, set up 1 state. Yeah. So here I just wanted to show a couple of basic functions that are available through the library. And now the next thing will be to show off the next experiment that we're going to do. Here we're going to measure the qubit many, many times, and we will compare the measured values with the theoretical probabilities that we should expect after having the state set. Okay, so let's go on to experiment 4. Here I will import the same library as before. I'll also import some math libraries or math functions from the math library. That'll help me out in calculating the theoretical values. And also for plotting, I have matplotlib ready for me. So let's go here. Here I will set the delay time to be a little bit lower just so that it won't take ages to do this experiment. And again, we're using the same device here. Okay. So to start off, maybe let's go with setting the state to 90, 0. So theta will be 90, phi will be 0. And right after setting the state, we'll calculate the theoretical probabilities of measuring either 0 or 1. So let's go. Okay, now we have an equal superposition. And the next part of code is pretty much getting a for loop up and running, some interactive plotting going on also. Here, during every iteration, we will set the state back to its original state. We will measure, we will see what the measurement will give us, and accordingly, we will update this list with its probabilities. And at the very end, we'll be able to compare what we got with theory. So here we go. Okay, so we see that the qubit is continually being set into an equal superposition. We see that it's kind of leveling out here. It's about 50-50 as we expect. It's a little bit dynamic. Okay, but slowly and surely it is converging to about, okay, so here we got 0.48 for 0, and for 1 we have 0.52. And as we see here, it is pretty close to the theoretical values. If I ran this code for a little bit longer, here I only did 100 measurements, yeah, then it would converge to what we would expect. But now that you believe me that it's working as it should, let's maybe try a little bit of a more trickier state. Here we have theta being 60 and phi being 30. Let's see if it'll set the state accordingly. All right, there we go. So we'll run this cell once again, and this time we'll be expecting different probabilities. Okay, so it's going, it's going. Okay, so it should finish right about now. Okay, and here we see that we have the experimental values being 0.65 or 67. Comparing it to the theoretical one, it's a little bit off, but for probability of 1, it is pretty close to what we expect. We can run it again, run it for more iterations, and we'll see that it'll be consonant with the theoretical values. So let me go back into the presentation here. Second. Okay, so if you want to learn a little bit more about the qubit, we can refer you to the following links over here. You can see how the QLMS is integrated with the qubit right over here. There's also the qubit QKD for quantum key distribution that is helpful in understanding quantum cryptography. And also we have a couple of publications under our belt already when it comes to the qubit. Just recently, this one shown here, and very soon another one too, and also more to come, of course. And maybe you were fortunate to see us already a little bit earlier at the Copernicus Science Center. We ran a popular science workshop called How Does a Quantum Computer Work? And among all the setups there, we also had the qubit up and running. Um, and you can also watch a little video over here to see how it went. And also, if you want to learn even more, I can refer you to the AIQ Lab website, also to our YouTube. Our YouTube hosts quite a bit of videos on experiments with the qubit. Oh, and as well as our LinkedIn, you can find out when we're planning any new workshops and so on. But with that, I wanted to thank you for your attention. Thank you for your engagement. If you have any questions, please let me know. Thank you.
Okay, great. Thank you, Konrad. Okay, so now it's time for discussion questions. Do we have any questions? Let me check on the chat. You can also unmute yourself. There's a question from Mohammad Reza. Can the emulator account for all the possible types of relevant noise, and also when comparing the theoretical versus experimental probabilities in the demonstration, the difference was somehow noticeable. How many iterations are needed for the run in order to converge statistically? So actually, there are two questions. So we can start from the first one.
Okay, so I'll probably start off with the second
Second.
answer.
Okay.
Because it's a little bit easier. I'll tell you that maybe it's a little bit unfortunate that yeah, that is true. During the second run, it did vary quite a bit, but that's just how probabilities work. Sometimes it's going to be a little bit closer, sometimes farther. Well, it's just probabilities. When I was running the experiment, actually just before the meetup. It was like right on the dot. So yeah, it really just depends. If you want, if you're not convinced, I can run the experiment again. But yeah, it should converge probably within well, I can't tell you exactly, but it usually did converge within less than 100 iterations. And also when it comes to the first question, can the emulator account for all the possible types of relevant noise? Um, I'm not sure exactly. I'll tell you that it does account for example, electromagnetic noise, and also the noise that does get injected into the qubit with an external source. Oh, maybe that's what you meant. Yeah, the external source does not have to be a function generator. That was just an example. As long as you have the right connection, you can connect it to the qubit and see it well being imperfect. And that's just how it is with quantum computers. They're not perfect. They're not always going to follow perfectly the mathematical formalisms that we have posed. And that's just the reality of it. Engineering quantum computers is a very difficult task. And we're happy that we're at least able to show that part of it through the emulator. Um, I hope that answers your question.
I hope so, but yeah, Muhammad Reza, feel free to ask a follow-up question if you need. And in the meanwhile, there's another question from Bartek Gortat. Is the device built on commodity hardware or does it require custom-made building parts? This is an interesting question. So, um, Konrad, can you answer? You're muted, just in case you want to say something.
Oh, actually, to be honest, I'm not 100% sure, so I will not answer the question at the
Oh, okay,
moment.
that's
But
fine.
if you want, we're happy to reach out to you. Just contact us, give us your email, and we'll get to you with that question. No problem.
Okay. All right. That's fair enough. Thanks. I see that we also have Marcin Sadowski from AIQ Lab. So Marcin, perhaps you can try to answer, maybe on the chat, but you can also try to unmute if you want. This is okay. And in the meanwhile, I can see another question from Łukasz. Can two of these devices be connected in order to emulate systems with entanglement? Another interesting question.
Mm. That's a very interesting question. And right before I answer that, I actually provided my email here if you want to check it out, Bartek. So just contact me and I'll get back to you with a confident answer. But when it comes to emulating entanglement, yes, it is possible. It has been done, which is really cool. Right now, we were just showing one qubit off, but yes, you can connect it with more, as I said. And yes, it is definitely possible, which is really, really cool.
Mhm. Okay, thanks. This is very good, actually. All right. Do we have more questions to Konrad? Konrad, can you maybe I will ask one. Can you or do you know what are the next steps or the next plans for the development of this device and in this general infrastructure that you have? Are you aware of some specific plans or goals?
I can say that we definitely want to um, work on educating when it comes to quantum technologies, not just the qubit, but in general with the other products that we have. Fortunately, the previous workshops at the Copernicus Science Center went really well. We're really happy about that, and
Mm-hmm.
I know in the future we'll just try to get more outreach, try to get more people interested in quantum technologies because there's a very big future for it for sure. And we feel like that's a market that we can definitely work on because unfortunately, um,
Mm-hmm.
that area can be improved.
Okay,
So we're there to help out with that.
this is good. And as we have many people from Poland here, but also from other countries, are you looking for some partners, collaborators? Do you see such options? Mm-hmm.
Ooh, I'll probably reserve answering that, and I'll say
That's
I
fine.
do not know. I do not know
Okay,
at the moment. Yes.
okay,
Oh,
that's
I
no
actually
problem.
just got a message from Marcin, the head of AIQ Lab, and now I can confidently say yes.
Yes. Okay.
So there you go.
Okay, yes. So just in case if you are interested, I know that the team from AIQ Lab is also looking for some partnerships, collaborators. So feel free to reach them out if you have any questions or ideas. All right, but
Yeah,
maybe we have
absolutely.
some,
Just contact me,
yeah.
reach out to us through our emails on the website or to the email I provided, and yeah, that's
Mhm.
that.
Okay. There's another question from Sivaram. In the meanwhile, was the FPGA programmed with VHDL or Verilog? Do we require any specific hardware requirement for FPGA?
Oh, actually, I do not know how it was programmed. My experience with the FPGA-based qubit was actually purely Pythonic. So I didn't dig into the FPGA. But just to start off using it, no, to uh, you do not need to
Hmm.
do any FPGA programming for that. Oh, and we
Okay.
just got an answer from Jacek, who worked on the FPGA, and it is a VHDL.
Hmm.
So yes.
Okay, good. Thanks. All right. Do we have more questions to Konrad?
So is IQ Lab looking for people currently, like for example, graduate students who are trying to get into the topic?
I think so, based on the answer, it is. Marcin Sadowski confirmed. Marcin is the head of the AIQ lab, so uh, I think you can also try to contact him, even here on the chat on the Zoom. But you can also send an email to Konrad, and uh, he can put you in contact with the other team members. Oh, and Marcin has just provided his email address as well. It's Sonovero R&D.
Thank you.
Okay, good. Do we have more questions to Konrad? If not, then let me thank Konrad once again. So Konrad, it was a very good talk. Yes, congratulations. And I can see some claps here. Um, so yeah, before we finish, I would like to announce the next meetup. So let me maybe share my slides again for just maybe 2 more minutes. Um, So Mohammed Reza asked about the slides. So definitely we'll try to share the recording. I'm not sure about the slides specifically. So Konrad, maybe you can answer if you can share the slides as well. I'm not sure, so I believe that the team may need to discuss it internally, but definitely we received the consent to record this meeting, and we are planning to upload a video to our YouTube channel. Okay, so thanks once again for joining. Thank you for your attention. You can also subscribe to our channels, join our groups, follow our social media, and so on. Stay up to date. I would like to thank our strategic partners for supporting us. Once again, Sonovero R&D, QUBIT, Quantum.io, AIQ Lab. So this project was presented by Konrad, who also collaborates with Sonovero R&D and AIQ Lab, Onyx, and QUBIT. We thank our honorary partners for supporting us as always. And if you like our events, you can always donate our activities. There's also an option to donate 1.5% of your tax if you pay taxes in Poland. You can find the details on our website. And last but not least, I would like to invite you to episode 73 of our Warsaw Quantum Computing Group meetup on January 22nd. Dr. Julian Baglio from Basel, from Quantum Basel, will give a talk about quantum generative adversarial networks. I'm not sure if the exact title will be exactly as I put it here, but the talk will be around quantum generative adversarial networks. So this is one of the areas of specialities of Julian. So we are looking forward to the next event, and we invite you to join us. Thanks once again. Let me now stop sharing my slides and stop recording soon. Yes, thanks for sharing the link to our YouTube channel. And last but not least, wish you happy Christmas, happy holidays if you celebrate, of course, and happy New Year. And we hope to see you in 2026 on our next meetups. Thank you. Bye bye.
Thank you.